minutes is really, oh God, here is recording, is really just to, again, my purpose is to share some empirical paradigms and how we model it, at least in the practice of quantum cognition. Of course, like for example, Domenico showed today how we can implement some of the model using quantum computer. So right now, for the sake of understanding the mechanism of human behavior, we don't believe, we, at least the group of us, don't believe we do not need the quantum computer to do this yet. But I guess I do agree when it's more complex with the network and simulation with the maybe group level type of behavior, emerging because we don't understand them yet, emerging behavior, quantum computer probably will be very useful. But anyway, what I present today do not need any computer, like a quantum computer. You need some theory, maybe from your field, from your interest, from your research question, from your paradigm, and hopefully some kind of empirical questions, even data you might find in the literature. That would be fantastic. I guess, again, I'm taking a very pragmatic idea here, is that how to start, right? Because I constantly being asked those questions. How do I start? Where do I start? It's so high risk, right? Even I kind of persuade my students, like PhD students, do not do this kind of work just because they need a job. They need to do something more conventional, can find a job in some way. I'm sorry I say that, just because for those who maybe looking for academic job in this my field, and I see one of my colleagues, Susan. Hi, Dr. Susan, Professor Susan Klein is my colleague from communication. You know how conventional actually the field is. Most of the fields are right now. But anyway, I think still, I personally believe though, it's become, especially with the booming of computational power and people's more acceptance to computational language and so on, I feel like this is a field that maybe become more and more acceptable to most of you, hopefully, in a way. So if you will, at my talk yesterday, hopefully, and Emmanuel's work, and maybe through today's Peter Bruza's talk, I hope you will somehow more or less convinced that it's useful, at least to try to see whether quantum framework has some useful way. And I want to step back just because I was getting a lot of emails and comments on, why not the theory? Because there are a lot of other kind of mathematical structure and theories and problem theory and logic theories. Kind of loosen up some of the very strict rules of the classical probability. I think that's really good questions. And I guess at least my take is this. My take is that we already have a quantum theory. Why not, right? It's already come with all this idea, not only just mathematical formalism here, but also very coherent conceptual ideas as well, highly testable. So I guess my own feelings is this. I feel like this, why not, right? Because it's the concepts really resonates very well. Like Peter today, Professor Peter Bruza presented today, even at the philosophical level. It's a lot of things, maybe more agree more with what we have been doing and thinking. I think I don't know about you, but I think like at least for me and for many of my close colleagues and friends, we all think similarly, right? In that kind of philosophy, maybe more or less, but practically we use what we can. And right now, maybe a very appropriate, promising way is this quantum formalism. This can be used to do those quantitative theorizing, the formal theorizing of the work. But anyway, that's just a little bit of few comments, and I get it from the thing. Yeah, okay. So, okay, I'm just seeing chat. Okay, so let me present maybe. So what I'm going to do in this short 45 minutes right now is to show you a few examples and how we exactly did the model. And again, it's just a oversimplification of what we have done. But I hope this can give some of you who are trying to do empirical work in your projects right now to find your paradigm. So to summarize again, there are many reasons, but again, quantum theory is a general axiomatic theory, and it suits to kind of model and formalize, theorize the human judgment, decision, cognition, our thoughts, our language, and so on. So it's actually more aligned with what we typically verbally thinking, but just maybe for some people, some scholars and researchers didn't or haven't realized that there's such a formalism out there yet. And this now commutativity of measurements, concepts, ideas, and in the theory really is essential, right? So it was, as mentioned yesterday, there has an interesting history, and we found it's very useful as a way to compute how things are constructed, like verbal language, thoughts, psychological measurements, and so on. Maybe like identity, maybe thinking about the formation, construction of a personal identity, but also for some of you, maybe the group identity and so on. Okay, the third is that the vector space representation probability really actually already agrees with the multidimensional space models of cognition. There are already quite many cognition models using multidimensional space, like machine learning use vector space. But like Domenico said today, do we need the quantum? So then going back to the number one, at least my feeling or my perspective is that I feel quantum theory has something, of course, useful to understand the observers, right, of the universe. Not only just the formalism, but also the concept and philosophy. So let me see. This is better. So now you have seen those kind of model quite many times through the talks, through the work, who work with such a cognitive model. And again, I want to say it's just because a few of us are using this kind of approach, and there are other people doing quantum cognitive models actually do not model the states updates this way. But anyway, those of us who come more from the cognitive aspects like this approach. So let me use a slightly different question than this Clinton and Bohr question. So actually, this is quite the, maybe very relevant nowadays. So this is a question actually from the Gallup poll as well. So it's a question asking the respondents, do whites dislike blacks? Yes, no. Then, for example, in one of the empirical data from Gallup poll, 500 national representative people said 0.4. About like 40% of people said yes, yeah, whites dislike blacks during the time. And then if you repeat this question after answering yes the first time, oh, did I play? Yeah, it's all right. Okay. It's right. Now, if you repeat the question after answering yes the first time, once again, do whites dislike black? Right? So what our intuition is that, yeah, it should, right? Just repeat is what's in the quantum theory collapse effect collapsed. So now it becomes whatever you're becoming this being. Now your answer is more certain, like yes. So now, if you have to answer a slightly different question, which is, do blacks dislike white? So you switched. Because before you're thinking from maybe the perspective of the whites, do white people dislike black? But now you're trying to put your shoes in black people. Then do black people dislike white people? So it's kind of changing in perspective. So right now, so in the model, you kind of rotate this evaluation space vector space from the green to this red. I found if I do play in the keynote, my mouse doesn't work on the screen anymore. But now you can see you rotate your evaluation space from the green to the red. And as you have become very familiar with now, maybe through the math workshop with Jacob and Michael as well. So now in this empirical data, the probability you say yes to white people dislike, like I say yes to WB, white people dislike black, and then yes to black people dislike white. So it's yes to white hostility and then yes to black hostility is 30 probability 0.33, 36% of the population, the sample. So that's this empirical data. So then if you just use this toy model, right, this is just like hypothetical right now, like I'm just trying to show like we can reproduce what's observed in the empirical data. So now what's on the left is what's shown, right, in this the probability say yes to white hostility and then yes to black hostility. Then it would be 0.33. So people say yes, yes to both questions in that white hostility first, and then black hostility is 0.36. Interestingly, if you use the exact same relation of the green evaluation space and the same rotation to the red evaluation space, and the same, this dark blue line is the initial state, right? The same initial state. But so what's only changed here is the order of the two measurements. So now on the right-hand side, if you ask the black hostility question first, and then the white hostility question, then by this model, you can see, sorry, my mouse doesn't work, but hopefully you can see. Let me just get out of this so I can show you. So you can see now which means now you're familiar with this kind of terminology, it means like you project your initial state to this evaluation of the black, yes, black hostility, black people dislike white. And then to the green, yes, white people dislike black people. So yes, yes, still yes, yes question to both questions, but just in a different order, black hostility first and then white people hostility second, sorry. Then you can see this probability is really dramatically decreased to 0.12. So this is just a quick toy example to show how those kind of sequence of measurement really matters. And we knew already, right? Like this is something I think any of us doing data with human know this would happen for many cases, for some cases at least, quite natural in our thinking, in our thoughts as well. So by the way, you don't have to be those kind of questions, right? For example, the empirical data paradigm we have done is including something like a narrative. For example, the persuasive narrative, if you say the first argument, then second argument, versus you say the second and then the first, that makes difference. Now let's take a look at the real data and real model here. Some real model, some already mentioned yesterday already. So as I talked yesterday, actually this kind of one of the early, not the first, but one of the early data we worked on is so I just quickly went to look at the literature in the public opinion research that I ever found order effects. Of course, there are many, and David Moore was one of the people really more systematically review those literature. So of course, those are typical and those order effects not only in survey question, but in many other kind of human data, like the order of the probability judgment, inference of the probability judgment, like I cited here, the conjunction, disjunction fallacy, and so on and so on. And order effects of document relevance judgment as well. So this is more relevant to like Peter Bruza and maybe Domenico's work here, like retrieve, like for people working on informatics, information science, like this is Wang's paper as well. It's like how the order of document relevance judgment, for example, when I search and retrieve information, when I say, I want to search here, apple and lunch or apple and stock, right? What do you mean by this apple? The apple of the fruit or apple of this brand? So it's really quite relevant in many things we do because we do it in this sequence. So typically in the, at least the psychology and social science literature, those are typically the noises or errors we try to, in a way, minimize or cancel out in our statistic models or in our design, such as in experiments, we try to randomly assign people in different conditions, different treatments, so we cancel, kind of try to ignore those kind of effects in our final readjusted data. So, but really here is that we believe those are evidence for the essential constructive nature of human measurements. Actually, they are not trivial, they're essential. So help us to know to test and to model, formalize the incompatibility and compatibility of measurements in our human life or human research. And again, I said yesterday, actually, those are, again, quite a commonly kind of intuitive and theorized in social psychology, for example, Professor Schu's work on the constructive view of attitudes and so on. So, but the quantum theory helps here is to give us a very elegant way to formalize those intuitions so we can test them and do better prediction and know when it matters and so on. And then maybe have an intervention and prevention in a lot of ways. So that's touches some really good question raised from the audience that what's this for, right? What's this is good for ethics and for changing the society and so on. So I just maybe I would say simpler level, maybe low, high influence level. At least it helps us maybe to understand, for example, how misinformation was passed on, how persuasion was really happening, so we can use those for social cause, like not persuading people to buy things, but persuading people to do good things, good deeds, for example. So, or prevent the bad things from happening, like Domenico was saying, like preventing, maybe negative or bad political campaigns. Actually, that's quite a well-studied, widely studied subject in political communication. So yes, I think there are a lot of opportunities here. So, and I want to present, quickly this model, which I skipped in my talk yesterday, but however, you have seen that in Emmanuel's talk and today slightly from the Domenico's talk. So the same model, the same kind of model idea is playing a mirrors of other positive phenomena as I summarized yesterday. But of course, when you really implement this in a parameterized way and competing with other models is much more complex. And I guess another question I forgot to ask Domenico, for example, beyond this paradigm, something I will show you, but not the model, but the literature and the data. Like for some decision models, luckily, we do have much better developed formal models decision, right? Like how to implement the utility function, how to implement those prospective theory in the model and so on. So we have something way beyond this simple, just rotate a few vectors, and there are dynamic version of it, and that's much more complex. And I have reference here and from yesterday's slides, and I'm happy to provide, if you're interested, if you would like to reach out and ask me, can I find something on this question? And is there a model there already? I'll be happy to, if I know, to refer you to those places. So there are much more complex models. So I want to just make sure, like what I show here, and actually people have showing through the talks are not really the whole complete model. Those are kind of the more like visual and toy, and actually the presentation of the two-dimensional model is wrong. It's just like for toy, simply for the sake of simplicity here. Okay, so what does this real data show in this white and black hostility? Is the data is like this. In this, sorry, I want my mouth back, so I'm going to get this out of the presentation mode. So hostility between white and black people. So for the, you ask how do you think blacks dislike white? So BW order. So actually ask black first and white first. If you see that, for example, people say yes, black people dislike white. No, white people, in this example, white people, say no to this question, white people dislike black, right? Because you have, yes, white people dislike, no, white people dislike, and you have yes, no for the black hostility as well. So you basically have a 2x2 table, very simple situation. So yes, you'll say yes, yes to both, yes to in the B question, but then no to the white question. So let's take a look at this one. So empirically, a big difference occurred, for example, in the situation when white black was a question order. So people say, no, white people, white people, do you think white people dislike black people? No. Do you think black people dislike white people? Yeah, there are in the sample, 16% something. Okay, so now in the other order, the same response, but to answer the black, yes, black hostility first, and then no white, then it's reduced a lot. So it's kind of intuitive if you take a moment to think about this. What this means really is that, yeah, if you ask me, do you think black dislike white? Yes. You like white people dislike black people? Actually, no. Less people say that, right? So compilation is smaller. So this is how we define in our own model called context effects. And you can see we can do this for all the 4 cells for question sequences. So for example, in this particular data set, the big difference occurs in this 2 cells, right? When they have yes, no, no, yes situation. But there are slight difference here too in the yes, yes, no situation. But those are kind of statistically testable. And you want to see how we statistically test them, you can read those publications we have. But anyway, there's significant order effects. And then if, of course, like we can say a general n-dimensional quantum model prediction is what we mentioned. Actually, in this particular publication and early practice, the focus is on to test whether this is simple model, something simple like this, right? Just assuming a rotation and presentation like this can produce order. And we mathematically derived this theorem called Q equality, which means the probability of yes, no, no, yes, like 2 different answers to the 2 questions in the AB order should be the same as say yes, no, no, yes to the BA order. Like I said yesterday, if you take a moment to again think about this, why? Psychologically, I wouldn't think about this at all, right? I wouldn't expect this. This is completely come from mathematics, and we show the proof in the publication if you're interested in read. Actually, the early publication, this one, and more elaboration on the second publication. But anyway, it's just a totally derive a testable kind of quantitative relationship based on a quite a simply assumed model here. So yeah, for this data set again, we can test the QQ equality, and yes, you can see actually they sum up in this particular example. In sum up, they are indeed is 0. Of course, with the statistical error here. So statistically, the difference is not significant from 0. So they are 0, right, statistically. So, but anyway, so that's what we did is that together, like I mentioned yesterday, finding just, blindly just go to find whatever we can find. No cherry picking, no anything like a prior. Just go to find whatever possible. Actually, it took a year to find trace down all the data and be able to make sure they are very accurate. Because over a decade, even for Pew, which is such a influential and most respected, one of the most respected public opinion research institute, sometimes the data is hard to retrieve, the raw data. So I want to make sure, so we gathered whatever we could with the 70 national survey data over the past 10 decades at that time. And we are able to secure 70 of such a situation that asked the AB, BA kind of situation. And so the statistic test show actually it's true. There is a significant deviation from the order. So it means like there is significant order effects. And when we test the QQ equality, and like I said, it's so testable, right? It's so simple. You just go to data, make sure you get the right data, and get this compilation from this data, get this, know to those people the percentage of N, say no to A, yes to B. What's the proportion, right? Just add them up, see whether they equal to this one. So statistic tests show actually is true, supported. The QQ equality was supported throughout the 70 national surveys, and those are national representative survey. So I guess for some of you who are thinking about the social level data, I guess this can be one, maybe something like maybe one way at least to test something more social, I guess, more social, right? So it's at least it's not in the lab, well controlled, manipulated data. It's really out there. It's just this national representative sample, randomly split, had ABBA model, kind of like a large field experiment in some way. So this is really far away from what I typically do and what cognitive scientists typically do in the lab with the sound of trial with the very well-controlled stimuli. But anyway, I'm just trying to give everyone a little bit idea. If you're interested in social lab, at least maybe this, maybe not as social as you wish for, but at least something beyond the typical lab experiments. And so that's one way. So, and it's so testable, I said. So actually we were very excited about this work just because it's so hard for social behavior scientists to find anything that's parameter free and can be extremely exact test. It's an exact test because there's no wiggle room here. It's just this plus this has to be 0. There's no wiggle room here. It's not a bigger, higher, slower, quicker, those kind of prediction. It's just like it has to be equal to 0. So this is extremely testable. So we're happy about this. And then, as I said, then we did some other things later on. I didn't put my reference here, but you can find that from yesterday, my presentation. Then we parameterize the model so it can be more general, like those cognitive model. Then we can estimate the parameters to more complex question situation, like 1 to 100 rating scale. Because that's, for example, typically people use in social behavior science, like how much you like someone from 1 to 100, from 0 to 100 and so on. So that's much more general and if you have a question about those kind of models, I'll be happy to address the question. So that's the typical cognitive modeling. Then we estimate those parameters. We compete with the more classical model. Like in our case, we competed with the most maybe the state of the art of the model in decision making with a dynamic model. It's also a dynamic model. It's over time. It's the decision can evolve over time. So we competed with the random walk model, like diffusion model of the field of decision making. So that's another application. So, well, that's something I feel like, again, I will show one example at the very end. That's another approach I feel that maybe we can do with social level, with the population. Hi, sorry. Hi, thank you. Hello. We can do is that using, if you are up to those kind of tasks, and you can use more the ones like Bayesian or hierarchical Bayesian, like a Bayesian kind of estimation to estimate the parameters for all the individuals, and then maybe you can, those initial state and relationship between those evaluation spaces can give you very meaningful, and also maybe rotation, the way the rotation occurs, right? Because we can build, for example, in our practice, we build those typical psychological decision computation models there with the utility function, those kind of things there. So then you can have something really more situated in your own theory, like your topic theory there. So that can be useful. So that's something I will be happy to talk more later on. But then I want to chat a little bit about why those kind of model is so useful, right? Even without doing this parameterizing or the hierarchical Bayesian estimation and those kind of things, is that, for example, with this ABBA paradigm I just presented, and there are colleagues of, and I'm happy about their criticism and challenging about why AB and ABBA would occur. Why? What's they challenged me with the sort of experiments, as I mentioned. Is that if you ask A, B, and you ask A right away, then it shouldn't matter, right? The A shouldn't change because you already, so intuitively think A just shouldn't change. Actually, those people who asking the questions they all have background in physics. So they're typically using thought experiments to think about those questions in a way. So as you said, I said, okay, I'm not sure, right? It could or may not. I don't know. I mean, empirically, it's really empirically testable. Because AB, it could have a sequential measurement like what we presented here. But I believe that also can interfere or not. It depends on the nature about the measurement, is compatible or not, right? If they are incompatible, you're familiar with those concepts now. So if they are incompatible, then yeah, A would disturb B, B would disturb how you think about A again. So there would be a change in A prime compared to A. So if A, B are incompatible. So then, like really the design is just so simple, straightforward then. So then I did empirical study here. So using our example here, white and black example here. So again, maybe at time 1, we ask the white question, A question, do whites dislike blacks? And the B question will be, hey, do black people dislike white people? Right, now, given that you have just thought about how and whether or not black people dislike whites, what do you think at this moment, do white people dislike black? So it's the A question, but you are already kind of collapsed, right? You already addressed some of, give some question, you're being measured, you're feeling certain, right? About this, your answer, you're thinking right now, do black people dislike white? Right now, would that, make difference on question A? Do white dislike black? Right, different from A again. But of course, there could be all tons of problems. Then actually, this I just want to set out of this publication again to chat with you about a few personal experience, because I found it extremely challenging to design experiments that can gather data, read and test our theoretic thinking. And we do have a lot of cases when our theory predicts so well, but the data just not there, just too noisy, and we can't have those quantifiable data or clean data as we wish to test the theory. So, for example, here I just literally copied what I did, and it worked, at least for my purpose. So I indeed try to at least encourage people. Now, given that you have just thought about how whether or not Black people dislike whites, what do you think at this moment? So give people a little bit, make sure, like, because there are, for example, phenomena in psychology called people want to be consistent with their answer. Like, you just asked me, now you ask me again. I want to be consistent with myself, so I appeal to be like a honest or rational person or like sensible person, right? So here, I kind of just put this word there. I don't know, because I didn't use eye tracking in the study, but at least give people a permission to say, yeah, just at this moment, what do you think, right? So anyway, I just want to give you some down to the earth, like those kind of things that sometimes was buried in literature. Sometimes we can't reproduce people's work because we didn't do exactly the same. Yeah, because it's so contextualized in that lamp, in what the lamp did. Okay, so now go back to this. What does this do? Is how do we test this, right? Ultimately, my question is that how do we test this? So let's take a look at the toy example again, just what we have shown. So we showed the probability. If I just start from this eighth initial stage, and you ask me, do white people dislike Black? And I say yes, the probability is about 0.4 in this toy example. And then if I just repeat this question right away, because I'm already collapsed on this subspace. So you ask me the same question, I'm here, I'm still in the subspace, I collapsed. So let's repeat. Now, if I already said yes to, Black people, but if you ask me, this is what I showed before this, but I didn't show the whole cross line here. But like, if you ask me, evaluate against this red evaluation space, which is a question about, do you think Black people dislike white? So I already collapsed down this red space, right? Then if you ask me whether the white people dislike Black people, then actually my probability change compared to repeat is order effects, because I'm not in this space anymore. You rotated me away into the red space, right? That's the idea. So you can see, actually, so initially, if you look at the style at this, then you can see, hey, really just rotation, right? And it's true. In those dynamics too, it's really how we theorize and estimate the parameters in the rotation, how we construct the rotation. It's really the key here. But anyway, to make everything very simple right now, if you look at this, what's relevant here is we can see that inserting in this ABA order now, ABA, insert this B between A and A prime, between A and A, it's really A, just A and A, right? But I put A prime, so we know it's the second time the same measurement was used. So between the two A questions, if we insert a B question in between the AA, really this just reintroduce uncertainty about this A question again. If that makes sense, this is just literally what this Heisenberg's uncertainty principle. Right now, you're certain, if now you're certain about your evaluation about Black's hostility in this red space, you're not certain, so certain, at least you lost some certainty about this radical green question now. So that's the psychology intuition, right? That makes sense, right? If, again, I'm talking about if AB question, the measurements are constructed, are something, we feel quite uncertain, at least not as certain as like you ask me about age. For me, my age and my gender, I'm quite sure, I'm 100%. So it's compatible, right? I store that knowledge in my brain. But in this case, I don't, because you ask me, how white people think about black, black people think about white. It's kind of a little bit constructed, like something I don't really have the firm property in my brain. So that's a prediction. So what the prediction really does is this new prediction. So I want to show this part, of course, is quantum theory, but then how do we test using human data, right? So here is what we add to the literature, what we tried hard as a social behavior scientists, like to test the idea in a human data context. So, okay, if you think about this, it's really about how you rotate away, like a panel 1, panel 2, and panel 3 are 3 examples. If mine somehow, so it really depends on relationship for each person or for this group of people in general, how their evaluation space for the Black's hostility, according to the green evaluation, the white hostility evaluation, right? It's how far away they are. It means, in a way, psychologically, what this means is that what are the 2 questions related in a person? Because maybe for some people in some culture, right, just like extremely correlated, like they don't even rotate much. Like for example, in this example, the rotation is small. If I think one kind of people dislike the other people, then other kind of people just dislike you as well, right? This is very, very much tied to personality, maybe culture, characteristic, and so on. But maybe for some other people, it's just very far away between, it's a really far distance, it's big rotation between the evaluation space. Maybe like it's just not correlate, like, what do you think about me really don't have much to do with how I treat you, maybe, right? In a lot of religions, there are such a belief as well. It's interesting, right? So for example, like some simple examples is like love, right? Some people believe, I only love you if you love me, right? Some people are like, oh, I love you regardless what I think you love me a lot, right? So there are different philosophy and different beliefs about those kind of things. So let's capture this kind of psychology intuition here, is that how one evaluation space is from the other. And by the way, I want to reiterate that this is just toy model, like 2-dimensional. It can be high-dimensional, n-dimensional, and this is in this more general paper in Psychological Review. I kind of mentioned at the end of my talk yesterday, which can, go up to, the dimensionality you need. Okay, that paper is more general. But anyway, here, so that's according to the ABA paradigm, really matters here is this intuition. You would get in this prediction, which is new prediction that's we generated from this AB model, now used in the ABA paradigm, that increasing the rotation of the Black hostility would increase the interference effects, which means it's different from the other one. Interference effects, it means statistically, it means it will decrease the correlation between the answers to the questions. Right, sorry, it means statistically decreasing the correlation between the answers to the questions would increase interference. It means the correlation between the red and green evaluation, the Black and white hostility, from left to right, it increase, the rotate away would increase your interference effects, which is the context effects we define here on the A question, right? Because you can see this is 0.9, now it's 0.65, it's 0.36, right? It's just like shrink in this example. Again, just a particular one example here. So that's really testable, right? Empirical testable, so easy. So without feeding the model, right, you can just test this prediction again. So here we just get 300 some people, did a quick study, but not that quick, just because we want to make sure we gather quite many data sets as much as possible without making the people too exhausted, right? So we got this kind of ABA kind of paradigm, asking A question and then B from 12 pairs of issues. How did I select the 12 pairs issues? From literature, public opinion, research, and psychology? Again, because some are just notoriously know they're incompatible. Like it's like, do you think the current president doing a good job? Yes, no. Are you happy with what's going on in the country? Yes, no. This is just typical political public opinion question from Pew. And typically there is order effects. Why we pick the things that produce order effects? Because in this case, different from the prior paper that we just go to get any data, but now we want to get the measurements. We know they're psychologically, right, in this sense, incompatible, right? Then order effects, if A and B, B and A had order effects, it's an empirical way to test incompatibility, right? So they are incompatible. So we want to make sure A and B, B and A should be incompatible. Because if they're compatible, then there's no order effect. And then of course, everything is just like classical probability predicts. So that's why we pick the questions with order effects in the literature at least. And then we rated them using something more complex, like 0 to 100 scale. So those are the pairs of issues like, what do you think about this Democratic candidates right now? Whoever was this president, like this state or presidential candidates, right, at the time, and what's the perception of this Republican candidates, right? So those kind of questions. So then first, let's take a look at whether even A change. Good news, right? Because the people criticized this AB model was saying A shouldn't change. In their thought experiment, A shouldn't change. That's too crazy. But A changed. So A asked the first time to A asked the second time, at least the mean deviation across all the people, 325 people, is 10 standard deviation units. So it's quite a lot of change. And 25% produce a large change. So some people change more. So that's something interesting. I think, again, something I hope can give those of you who study social phenomena, maybe like more social level, large population, can think about the different ways you can critically test the culture difference, group difference, society difference, and so on. But anyway, so you can see people are, right? And there could be people who never change as well. But you can see it's a distribution. Some people change more, some people change less, right? But people overall change 10 standard deviation. So then that's our prediction. Let's test the prediction. So good news, A and A change. So that's the interference effect we defined in our empirical work. So indeed, the interference from B. But our prediction, just to recall this, our prediction is that the last correlation between the green and the red, right, the two questions, two measurements, then the bigger the interference effect, the bigger are those people, right? Bigger change. So this is a test of it. So if you take a look at this, it's just simple correlation, but it's really consistent with significantly supporting our prediction. This is a new prediction we generated. So on the x-axis is the correlation between A, B. So it means like how much rotation from A to B, right? And the y-axis is the correlation between the A and A prime. So the measurement after the first time and the second time. So it is a significantly positive correlation, 0.86. So it's indeed when A and B, that means that they rotate far away, the interference is greater. And when the rotation is small, it's smaller. So this is one example. So since I'm running out of time, And I just want to show the same idea was used for conjunction, disjunction, probing, judgment error, right? This was talked by Emmanuel yesterday. So it's a very similar idea to using, again, this is toy model, but the cool thing about this is that if we know the conjunction, disjunction occurs, then you would predict a range of predictions as shown here. So once you know this A-B events have those kind of showing this, you violate this law of total probability, which is actually what Dominica was showing in his talk today. If you know why is the law of total probability, by the way, this is the foundation of the Bayesian network, the Bayesian model of cognition, right? The Bayesian rules. So if we violate the law of total probability, then we observe this conjunction fallacy, this famous Linda problem. Yesterday, Emmanuel went into detail. Then you would predict a range of things like this. You would also know in the same kind of concept, the measurement would create conjunction, disjunction constraints like this, would have positive dependency like this, would produce conditional probability like this, and so on, so on, so on. So it's very testable. I just want to highlight that. And the same model has been used to test another idea of the interference of categorization and decision. Actually, this was my first empirical testing in this kind of quantum cognition idea, because this was totally inspired by the two-slit experiment. And if you're interested, you can read those two papers. We ran a series of 6 different experiments to test this idea. And this paper published in Cognition actually presented really the full model of this work. So what this does is that if you think about a categorization question, you look at the face, you categorize it, and you decide how to interact with it. For example, you categorize this person as good guy, bad guy, and then decide to be friendly or aggressive. It's kind of a two-slit, right? This was the first, this two-slit. You don't know whether it's good or bad, this two-slit. And this decision was the wall at the end with the fountain, right? Hit the wall to show the distribution. Okay, so this experiment was just meant to, so we ran a range of them. I just want to, the data are very interesting. So it's really interesting, right? Because we can test, you measure during, you can observe which category, which is two holes or two slit, right? Two slit, good guy or bad guy, it went through without. Now in the second condition, you only ask the person to decide. Without asking the person to categorize the face, you can say, do you want to be friendly or aggressive to a person? To give us a very interesting phenomenon, very interesting even. Why? Because, for example, people, this is just one of the examples, okay? Because there are so many examples. So one of the empirical data is that when it's a bad guy, for example, without a categorization, so that means without observe which category you want to put this person in, good or bad guy, you just ask the person, how do you want to respond to the person? People are really mean, right? Because it's this is the probability of being aggressive, right? So sorry, I have to take a look at the notation for so many A. So this is the probability of being aggressive here. It's really, people are really mean. People are aggressive to people, right? Without even knowing the person was good or bad. Actually, people are more aggressive than what? Then you already said the person is a bad guy. You see here, here is the conditional probability. Here is in the season D condition. So it means I already said you're a bad guy, and what's my probability to be aggressive to you? Probability is 63%, 0.63. And when without, right, observe, we don't ask the subjects, the respondent to tell us, do you think this is a good guy or bad guy? They're just extremely aggressive. They are more aggressive than when they already thought the person was a bad guy. So it's very interesting. So we used a model to explain it. And this is one example, as I mentioned, we implement those utility function, those entanglement between those perceptions and so on, the entanglement idea. So anyway. So the same model, the same idea, then we used to model like the violation of the sure thing principle again. So all this kind of violation, fallacy, irrationality problems we have, right? Like humans are so strange. So like, for example, the famous Prentice dilemma again, so on. But I will skip those. So also we used to, in a recent application, we used a similar model to model the centipede game. Centipede game is quite a complex game with 6 stage game. In this particular example, my lamp implemented a 6-stage one. So it's dynamic with 2 people, you have to rotate what you think, what other people think, and then go on with 6 stages. So it's quite complex, more like the real life situation where you interact with people with multiple rounds. So there are some complex, not complex, but just like at least more than that rotation we showed, some dynamic computation here. And you can read in the publication. I'll be happy to chat with you in person if you're interested. But I want to emphasize it all goes on to this basic principles that I've been talking about here, about how present a superposition, how the measurements is sequentially produced if they are incompatible, and how the interference can occur. And I believe Michael and Jacob said in their workshop about how the interference right, was formalized in those kind of models. So this is another question and another example. The same example was used to, the same idea was used to estimate 2-stage gambling paradigm. I want to highlight this one. Is again, as something I mentioned, this is one we used the Bayesian estimation method to model individual data. So then we can look at distribution of the data and so on. But this one, why are we doing so? It's because it's challenging from people saying, hey, of course, quantum model is more, quantum model is much more better because it's more complex. It has complex number anyway, but actually we show actually it's not more complex by using the Bayesian estimation, because Bayesian model estimation actually, right, take into account the complexity of the model beyond just the number of parameters, but also the mathematical functions and more. So, but I think this I want to highlight is because if you want to see, if you're interested in much more sophisticated computational modeling with the social phenomena, maybe one approach is also looking at the model estimation method, and maybe you can estimate the estimation of the distribution of your group of people on like some phenomena, some data you observe the data. So I have just stopped here. It's just so much more. And again, the ending point is that myself feel it's really useful framework. Peter Bruda presented beautifully that it's actually maybe more so to our philosophical take in some ways, like this is for some of us, and also more consistent with the concepts, just the theoretical concepts in the research area, especially those of us who study humans, right? The observers, yeah, actually we think so. Our verbal language, verbal theory has been talking about this, but just many didn't realize there's such a formalism out there already. And there are many other formalism, but this formalism has a cool idea about it's very coherent and it's so testable. It comes with the idea, the philosophy, many interpretations, and this clear math and computation tool. Thank you. Sorry, I went a little bit over time. Sorry.
Yeah, no problem. Thanks a lot, Joyce, to give us such a comprehensive overview over all the work that has been done. That's very helpful, especially to those who see it for the first time. So this
everyone. Yeah, and I really want to thank you, Jacob and Michael, took the task about the math tutorial and everything. And like I just want to again just emphasize, it's just so hard. It's not that if you know math, you can do this, or if you know you have the data, you can do this. It's just so much work, like struggling with how to develop the formal theory based on your own work right now. Yeah, thank you. I mean, I just want to again share, because those things published look so easy, but it's not, right? Just like all the struggle out there, just like everyone experienced now. So I guess I just want to more or less show more of the behind the scene. It's not that clean. It's not that easy either. Yeah. Sorry. Yeah. Yeah.
So,
the slides will all post on website. Matt was asking about the slides. Yes, of course.
Okay, good. And then maybe one question I had, because you mentioned it during your talk, and you mentioned something interesting that using this type of experiments, one can classify people into more quantum people and more classical. What type of experiments would that be? Has it been done?
Yeah, it's a really good question. Something like, I feel that's a low-hanging fruits. If we want to know those kind of things, we mentioned, actually people constantly mention this kind of idea. First let me say that in the early day, even from the day one, we thought about, just people are different. Actually, we're not expecting everyone is quantum-like, right? So actually, in my early experiments, actually, we put in a lot of personality, like traditional social psychology personality measurement there, including those cognitive capacity, reflective scales, which is so widely used, and people even, I don't know how accurate they can measure things now. But like, for example, Emmanuel mentioned yesterday, they found something, but we never, like in my data, we never worked. So it really depends on, maybe sample, maybe just because it used so much in those population, we measure. So, but I think, like, let me show this. I think the last, to me, I think one of the idea is like maybe the last example, this one actually, so this one, again, it's in response to the more cognitive scientists, right? Cognitive scientists just like, you're using complex number, like this quantum theory is so complex. So really the initial motivation would say, hey, like, let's use in quantum estimation of the parameter and say what it is. I will skip those details about what the paradigm really is. But anyway, we took some paradigm that's so well fit already in the literature, but not even just fit, but it has a beautiful psychology model, actually from Busemeyer lab, right? Like classical model. It's already so beautifully fit the data like 95% or whatever. It's like already done in a classical way, psychological, meaningful, consistent with all the psychology, decision theories, and fits data so well, right? It's like really good already. So then that's a good competitor to pick. So then we model using, anyway, I'll skip those ideas.
We cannot see your slides.
We can. Oh, sorry about this. Let me see. I believe it's this one. Yeah. So what I was mentioning was this paper. So we did a more like a Bayesian estimation on this model. Is because we picked a model and the data that's already has been done so well, fitted so well from the classical models. So then we implemented the quantum version of the model. So psychology intuition remained the same. Yeah, so this is actually a very famous paradigm in the literature from Tversky and Schaffer. Like, anyway, I will skip that part, but just but I want to answer Mike's question is that why this could be interesting. So in this one is because we indeed getting a lot of data from each individual, getting a lot of trials. So that's a luxury we could have. This is the backend Busemeyer 2003 data already has a nice data set, and they developed a very sophisticated decision model, fit the data so well and psychologically meaningful model so well, right? So it's not like as we mentioned today and in other situation, not just fitting the data. It's a theory, formal model, formal theory. So then it's really a competitor. So then we use the Bayesian estimation and we implement the quantum version of it. So what's interesting is do a comparison about whether the quantum or the for this case, the quantum and the classical version fits each individual better. It's like, so actually it's good. So actually in this particular data, 83% of participants favor quantum model. So it means the quantum version predicts 80% of those people better. And we can, of course, identify who and who and who, and maybe then, if you're studying religion, maybe study meditation, study some of the interesting things you're doing, or culture difference or language process, for example, right? It's so well known that language shape our cognition. So with different language, maybe it's just yeah. So for example, those are American people, students. 83% are quantum-like, but of course, which means the 17, at least in this context, they are more classical-like. So anyway, I think that's like one way we can do it.
Yeah, that's very interesting.
Yeah, then we can correlate with other things we do, right? Whether you meditate or not, whether what's your philosophy, even your philosophy on you like those kind of ontological stand and so on. I was just thinking like there was so much to do. So interesting.
Would you rather be a quantum or a classical? What do you think? Is it? Yeah.
Oh, that's a really good question, because like that's really a important question. I think I don't know whether I have a choice, right? Yeah, it's just what happens. I don't know. And now I even don't know what to cause it, right? Whether I was caused by something. But anyway, I feel it's not a simple question, because even in this, positive effects that I just shared, people so strange when they don't even know the person is bad or good, they just become aggressive in this particular test though. But however, in this St. Peter again, we found different pattern. It's much more complex. So it's not always the first question. So it's very sensitive, beyond those contextuality we have been talking about, but it's very specific to that particular context measurement. I think it's very specific. So I feel that's why study as observers of the universe, study the observers is so challenging.
Okay.
Yeah. Thank you. Sorry, I'm taking up your time on the math tutorial right now.
Yeah. Okay, we'll switch over. So if you just stop sharing.
Yeah, I'll stop that right now. Thank you, everyone, and I'm happy to chat more in over other ways. Let me stop sharing. And Mike, I'm so sorry. I have some other obligations. Actually, for my daughter, that's why I'm sorry. My daughter constantly was like coming over. So sorry, I have to take her to somewhere else, and I will see you tomorrow, everyone. Thank you very much.
See you tomorrow. Thanks again. Okay, so back to the math. We still have, in the principle, I think we still have 10 minutes, 15 minutes break, right? Am I right? Yeah, so maybe let's take the break and resume at half, something like this. Okay, good. Resume. Okay, welcome back to the day 3 of the math tutorial on linear algebra, and today's topics will be the following. So it's linear operators, eigenvalues, and eigenvectors and the Schrödinger equation. Okay, so this is quite technical already, but I will try to do it in a way that one gets again the main intuition and sees a little bit of the math and gets a taste for it. Okay, so linear operators, eigenvalues and eigenvectors. So operator, what is this doing? It is a map from a vector to a vector. So for example, A denoting the operator, and we will specify what it means later. So we have a vector V, and then we apply the operator A to B. That's how it's written. And if this operator, so this will just result in another vector. If this operator is linear, then from this follows that from knowing how V will be mapped to A times V, follows that if I map lambda, which is a number, times V, plus mu times another vector, then this will be mapped to the following, to A times V stretched by this factor lambda, plus A times W stretched by the factor mu. Okay, this is just the requirement of linearity. So you can also think of other operators, nonlinear operators. They will not. They may map a vector to another vector, but they will not fulfill this linearity requirement, which simplifies a lot. And quantum mechanics is linear. So in this sense, the mathematics of quantum mechanics is very simple. Then maybe we have this came up during the week. Operators fall into different classes, and the ones which are most important for quantum mechanics are the self-adjoint operators, the unitary operators, and the projection operators. Probably I've forgotten some, but let's first talk about self-adjointness. They are very important. Why? Because their eigenvalues are real and their eigenvectors are mutually orthogonal, and they therefore form the basis of a Hilbert space. So for those who are already lost, don't worry, we will talk about eigenvalues, eigenvectors during this lecture. And observables, which are measurement operators, are represented by self-adjoint operators. Well, we encountered them before, and we remember that the possible outcomes of measurements, they were described by vectors which were orthogonal. This is where the orthogonality requirement here comes in, and measurements typically are real, and therefore when you put both together, this will provide an intuition why the observables are described by self-adjoint operators. So the eigenvalues of observables specify the possible outcomes of a quantum measurements. This could be in physics, in a physics context, this could be position, momentum, energy, and their eigenvectors specify the set of possible quantum states after measurement. So we encountered this before already. So these are the vectors onto which the quantum state gets projected after measurement. Okay. Any linear operator A can be represented as a matrix that describes how a given set of basis vectors transforms under A. So once we have a basis, we can then represent this operator by a matrix, and we will see how this works. And then from this, it is then possible to determine how any vector transforms under A because of the linearity of A. So once we know how the basis vectors transform, we know how any vector transforms. So now, if this was too abstract, no problem. I will repeat exactly the same with examples. So say we have the following, we have a 2D vector space. So it has a basis consisting of 2 elements. And if this basis is orthogonal, then we can represent them by these 2. The 0 state represented by 1, 0, and the 1 state represented by 0, 1. We had this last week, like yesterday. I'm a bit tired today. And we can graphically represent them as follows. And by the way, Jakub, if somebody raises a hand or has a question, please let me know because for some reason I cannot see the panel anymore. I clicked it away.
Yep, no problem.
Okay.
We have Eva asking.
Oh, okay, very good. Yeah, hi, Eva.
I was going to ask, could we just go back 1 slide again?
Okay, sure.
Yeah. Just for a moment.
Okay. Yeah. Do you see it?
Okay. Okay, now it makes sense. Thank you.
Yeah. Okay. Good. So your question is answered. Okay, so now let's assume, just as an example, that A is acting on the basis vectors as following. So applying it to the 0 basis vectors, it's transformed into 0 plus 1, like a type of Schrödinger cat state. And applied to 1, it's 0 minus 0.2 times the 1 vector. So in pictures, just this, okay? So note here that we were starting with 2 vectors of length 1, so they would qualify as quantum states. And but after the transformation, they wouldn't. Their lengths may change. So and this operator can be represented by this matrix. Why? Well, because if we multiply this matrix by the first vector, it results in 1, 1, and if we multiply it with the second, it yields to this vector, which is just another way of writing these superpositions here. Okay, I hope this is clear. If not, please let me know. And we see that A is self-adjoint because what means self-adjointness? When you have the matrix representation of an operator, self-adjointment means the matrix is symmetric, and it is real along the diagonals, and the off-diagonal elements they are like complex conjugates. So here we cannot see it because the complex conjugate of 1 is 1 because it's a real number. But say we had an I here, like a complex number, then we would have minus I here. So this would be a complex conjugate. Okay. So specifying how the basis vectors transform is sufficient to determine the mapping of any vector. I've stated this before. So now we know how the basis vectors transform under application of A. And now we can go around the circle. We can start here and look at this vector and so. And when you do this, what happens? So you start at the blue here, and you go down, down, and then you go further around. So you see that under this linear operation, this linear mapping, the circle here becomes mapped into an ellipse. What is the nice thing with the ellipse? Can anyone tell me? Like the characteristic feature of ellipse. Otherwise, I ask you. Marcin, what is a characteristic feature of element ellipse?
It's a good question.
It's fine. So the characteristic feature is it has two axes, right? And the cool thing is there are, and you see this red state, it gets mapped to something different. The blue state gets mapped to something different, but there are vectors which get mapped to that they will point it to the same direction as before. They will just be stretched. Okay, and where are they? So in general, the vectors get rotated, stretched, and possibly flipped. But some vectors, they maintain their orientation and they are just multiplied by a factor lambda. And these are the so-called eigenvectors. Okay, how does this work? So this green vector here gets mapped to this green vector. So you see it's pointing in the same direction. And this is exactly aligned parallel to the principal axis, to the one. I mean, an ellipse has two principal axes. And for this vector, it gets mapped to this vector. So they are anti-parallel. So they point in the same, they have the same orientation. Okay. So these two vectors stand out. And if we were doing the same exercise in 3 dimensions, we would have an ellipsoid with 3 eigen directions, principal directions, and so on. And these are this is like a nice way to just have a representation or to think about eigenvectors. And the stretching factor by which they get elongated or compressed is called the eigenvalue. Okay, and now it makes sense why the eigenvalue is a real number. And just a second, Eva, and it can also be negative. So negative means it will flip its direction and be stretched or compressed. Okay, Eva?
So my question is when do we use these, or what's the application?
For example, if you do a measurement and you measure the position or the weight or the height. So the height of, say you have like different outcomes for the height of a person also. You do a quantum measurement. So then the way you would do this, you don't know the height of somebody before, and now you do a quantum measurement and the height can be either this or this or this or this. So you have 3 possible outcomes. And then
Related to Peter Bruce's
it's simpler. It's simpler because Peter was looking at different observables which don't commute, and we will talk about this later. But right now I'm just talking about one measurement, one observable, and you have a list of possible outcomes, and these would be the eigenvalues of these observable. And then you could calculate the average height also, which you would get on average. And you would just multiply this observable by the quantum state and then you would multiply it again from the other side, and you would get automatically the average height of which you would obtain when you would repeat the measurement several times. If you just repeat the measurement once or do it once, then you will, when you measure height, only the wave function will collapse on one of the possible eigen vectors of this observable. So, and of course, different observable, say height and I don't know, eye color or so, they will point in different directions.
Okay, thank you.
This would be the way to quantize or to translate a statistical problem in classical statistical problem into a quantum framework. Each time you measure, you first would have to think, how does my operator look like? My measurement operator, my observable. How are the eigenvalues arranged, and how long are they? It's another way of thinking about a model, about measurement. Okay, so
I'm sorry.
yeah.
So I have also a question. Is it something similar to a scalar vector in PCA, in principal component analysis?
Yeah,
there is also an eigenvalue, yes, and even the terminology is the same.
yeah, but in PCA you have it's based on a correlation matrix, and
yes,
there the eigenvalues can only be positive by definition.
yes, right. Yeah. Yes, okay.
But otherwise it's similar.
Okay, thank you.
Okay, so and remember, I think on the first day I mentioned that when it comes to the usage of quantum states in the context of classification, we cannot discern really whether like a quantum state V2 and minus V2 represent the same state, because we cannot tell about the phase here or the sign. So it's all that matters is like the orientation. So yeah, so then the eigenvalues of self-adjoint operators are real. I already mentioned this. I mean, one can prove this. It's not self-evident, but you can show that if a self-adjoint matrix always has real eigenvalues, they can be positive or negative, and the eigenvectors from an orthogonal basis of the Hilbert space, one can show this too. So this would be the green vectors, would be the eigenvectors. I don't know, there's work being done in the apartment above. I'm not sure. I hope it doesn't interfere with the sound. So in quantum theory, observables are represented by self-adjoint operators. Okay, I think I mentioned it 3 times by now. And the eigenbasis of 2 observables, A and B, in general differ. So this is what Harold, actually he didn't talk about this here, but what Peter was talking about, and also Emmanuel Bottos. So say we have 2 observables here in matrix form. This is the example we already discussed, and now their respective eigenvalues and eigenvectors. And now let's have this other matrix. So you see it's self-adjoint, it's symmetric, and okay, here the elements are all real. It doesn't need to be real, it can also be complex ordered. Okay, so we see that now the eigenvectors are different from here. Also the ellipse has a different orientation. So we can infer that these 2 measurements, they will not commute. There will be interference, just as what Joyce was talking about. So say these are the eigenvalues. They are incompatible. They don't commute. A times B is not equal to B times A. So there will be order effects. So one can also think about it this way. Measuring B will blur the prior measurement of A. So there will be a washing out effect. So say you measure A first, you will get either this or this. Then you measure B, you will get either this or this. So there will be these two questions will, yeah, I don't know, affect the previous outcome. And A times B unequals B times A implies that the commutator defined as A times B minus B times A is not 0, so it doesn't vanish. Just in case you have seen this expression before, it just represents this expression, this subtraction, and it's called the commutator. So for example, let's calculate this commutator. This is matrix A times matrix B. This is matrix B times matrix A. You just evaluate it. You will find this as a commutator, which is not 0. So, however, in contrast, when the commutator is 0, then these eigenvectors point in the same direction. And it says the eigenbasis is the same. The eigenvalues may still be different, it's fine. The both observables then are compatible and they can be measured sharply. There will be no order effects and no Heisenberg uncertainty. Okay, this is the first part of my talk. Are there any questions to this before we start talking about dynamics? If that's not the case.
Michael?
Yeah.
I just want to say that your sound is not perfect. I am not sure whether.
Yeah, it's because they work.
Okay. Yeah, we can hear you, but it's like slightly more problematic than the other days. But I think we will handle.
I could go outside, but maybe try this. Yeah. Maybe this helps. It's always when I give this talk that there's. But last year we had the same problem.
Yeah, I recall.
Okay, but I think it's as loud. Maybe it's even worse here, right?
We will see.
Better? I can hear it. Anyway, let's talk about the dynamics now. So now about the Schrödinger equation. So this is a Schrödinger equation, and by now we have a sense what it represents. So we have the state. So it's a differential equation. So it describes how a quantum system changes over time. So C of t denotes again a state, a quantum state, and it depends on t, on time. So it will change. And the way it changes is described by this operator h. Okay. So knowing the current state, multiplying it by the so-called Hamilton operator will determine by this linear differential equation where the state will be pointing next. And we know, can you hear me? Is it still okay? I'm trying to talk a bit louder.
Yeah, we can hear you.
Okay. So now a quantum state, of course, needs to be mapped to a quantum state. So this whatever is happening here, the length should not be changed. Okay, and we will see how this is guaranteed, and this requires the notion of unitary operators. So then we have the complex I here. This is necessary because without this complex number here, we would just have a exponential growth or exponential decay. So the length would explode or it would go to zero. So I and the notion of complex numbers is essential in quantum mechanics. And then we have the H bar. H bar, when it gives the degree of fuzziness. Of course, in quantum physics, it's a constant. It has been established. It has been measured. It's called the quantum, like the Planck constant. And it's a very small number, but it's finite. When H bar is zero, we are back into the classical. So, and in a quantum cognition or so context, it doesn't matter. We can just set it to 1. We don't need to bother about it. But yeah, so we will set H bar to 1. And so let's see whether all what we learned in the previous days, whether we can use it to understand how the quantum system changes over time. So it's just repeating what I just said. C of t denotes the time. No, the police is coming. I mean, it's really, the universe doesn't want you to learn about quantum physics. The Hamilton operator is sometimes called the Hamiltonian, and it has all the information how the quantum state will evolve. So of course, it is model dependent. I'm sorry, it's so loud. And this is where the modeling comes in. So there's no stereotype Hamilton operator. This is where you have to look at your system and then to design it so that it best describes the dynamics in your problem. Okay, and it describes how the state evolves when it is not observed. Because when it is observed, what happens? The quantum state will be projected onto observable, onto the eigenstates of the observable. Okay? But when nobody is looking, the quantum state never stays still. It always moves according to Schrödinger's equation. That's also an interesting difference between a classical system, which, for example, a nonlinear dynamic system, and quantum mechanics. In the classical system, states can settle into attractors. So in a quantum system, this can never happen. Always moving. Okay, Matt.
Yeah, so that just quickly raises some interesting question about preparing a system in a state before I've observed it. Once I've prepared it in what's called a state in the language, how do I know when, if this evolution begins? It immediately begins? You said it's completely always in motion, or but then it's not in the state it was at time 0, right? So I apologize. Yeah. I'm very ignorant. I'm not a physicist.
Yeah, it depends on your setting. So, of course, for example, you could in a physics setting, it's easier to tell because you could prepare the system and then you could prepare it in the eigenstate of a spin up or spin down, for example, and then switch on the external field, magnetic field, I'm saying perpendicular. Also, you would have a control when a certain aspect of the dynamics kicks in. But even without external force in the physics setting, the particle will always evolve according to the Hamiltonian of a free particle. So even then, this would be the equivalent of a particle just flying through the vacuum or so without external force. It would just do ballistic motion. Also, this is described by the free particle Hamilton operator. Of course, this is boring. So typically, you would set your particle into some structured environment, like a harmonic force environment. It would be the harmonic oscillator, and you place it there. You would know after a while, for example, it decays to the ground state, and now you could start your experiment. You could perturb it out of the ground state, inject energy. It will be lifted into excited state, then you observe how it decays or something. Yeah, but we are in a structured environment, so there's no such thing as just no Hamiltonian, as far as I can tell. Does it make sense?
Thanks.
And of course, the interesting question is what in quantum cognition also, what does the Hamiltonian mean there? Or in quantum game theory. Maybe Jakub will in iterated games, maybe they have looked at this. I don't know. Maybe,
how has that been described? Like that, how do people describe that Hamiltonian in those environments?
yeah, for example, today what we saw in Dominic's talk, all these gates, quantum gates, which were multiplied, in a sense, these were making up the Hamiltonian. So you see, the Hamiltonian can also be made up of a sequence, different times, different gates. So it's not necessarily a constant thing. It can change over time too. For example, in quantum computing, it would change over time. As far as I understand.
Well, if I can add one thing, in quantum cognition or quantum game theory, usually it's modeled by the static picture, so there is not much dynamics there. So like the use of Schrödinger equation, it's quite limited there. So we rather think of like projection or how, like, for example, changing the perspective, change the the context and so on, but without much dynamics there.
Is that due to, like, we're throwing out all the information we don't care about, and we're only focusing on something which is static for an interval of time?
Mm-hmm. I mean, sorry, Mike, go on.
Go ahead. Go ahead.
I just want to say that there is this like discussion. What does it actually means that quantum physics needs two descriptions of the reality? One which is described by these projection logic, and the second one which is described by this Schrödinger equation, which is continuous. So we have one picture which is continuous, and then we introduce this projection which somehow abrupt this like quantum state and throw it somewhere. So there is definitely discussion about what does it mean. I'm just saying that, like, in the cognitive science, the first one is used more often. It's also easier, and I would say that what Michael pointed out, it's not clear what Hamiltonian is supposed to be in cognitive science. Or if you are describing like language or classification problem, what would be the Hamiltonian of your analysis? In physics, it's energy. So if I'm not mistaken, or maybe I'm simplifying too much, but yes, easier interpretation in physics, or direct interpretation.
It just tells you how the state develops, and whenever there's processing involved, there will be Hamiltonian. Of course, the Hamiltonian could just be defined on certain discrete times. So whenever we measure, and then in between nothing happens. But this is the assumption. I mean, when we measure A and then B and then A again, like Joyce, what she presented, this type of experiment, and then she showed that geometrically what to expect. Well, what happens in the time between, right? Once, like, say you measure A first and B, and now you are in the eigenstate of the B observable, and now there's a certain time delay until you measure A again. Her assumption was the state will remain in the eigenstate of B until you measure again. Who knows? Forgetting can set in also. This is not captured. This would be captured by the Hamiltonian. The time, the dynamics in between measurement. Okay, Marcin, you have a question.
Thanks.
Yes, maybe not. I'm not sure if it's a question, but I have a probably very naive way of thinking about it and understanding that it's something like, let's have, for example, let's have a lake. And we are not looking at this lake, but somebody is putting a stone into the lake. And then we know that there are some waves, yes, which are created by putting the stone into the lake, but nobody observes this. And in some moment of time, a picture of this lake is taken. And from this picture, we can measure this waves, you know, or some other properties of this waves on this lake, but nobody observed it before, so we know that there is something like that, but we can measure it only after taking a picture. I'm sorry, so this is my that's what I said, that it's probably very naive way of thinking about it. But it goes into my imagination that I can think about it in more realistic. Yes.
Yeah. I mean, this is the proper way of looking at it. So when you throw something in the lake, the waves at the beginning, the lake it's localized, your excitation, and then it spreads.
Yeah.
And this is exactly what is described by the Hamiltonian. And then if you measure something, then you would put in like a grid or so into your lake, and you would measure, does a part, like, do I have some structure here going through my measurement device, yes or no? So you would change, you would interact with the wave pattern. So this would be observables. And then after measuring, it would again relax further, and you have the wave propagation kicking in again. This would be the Hamiltonian. Always what describes the dynamics between measurement. Okay. Of course, there are subtle differences between the wave picture of the lake surface, because this is a classical wave.
Yes, sure. Yes. So this picture was, I used the metaphor of a picture. I used only that it's stopped at one time, that it's, you know, that yes. So there is a dynamic in this process. However, we stop it at the moment, and this moment is pictured, and this moment is the collapse of this, let's say, process. Yes. Function. Yes. You say function, but I would say process, but it's the same. Yes. So. Yes, and when you measure, it's like you get the outcome, and then it's reset to the outcome. So this is the difference between the classical and also before measuring, you don't see any wave. Yes, you see nothing. You only see when measuring. So it's a very strange wave phenomenon. But it's helpful to start thinking. Okay. Thank you.
Okay, H is called the Hamilton operator. Yes, and it describes what happens, how the state evolves when the system is not observed. It defines your dynamical model, which is always a useful thing to have if you might want to make predictions. Right? H is self-disjoint, so we know what it means. And therefore it has real eigenvalues. In physics, this is motivated by the fact that H represents the energy. Energy is always real. Here, it's motivated by the fact that only if it has real eigenvalues, this differential equation will not change the length of the state. So we need this in order to preserve probability. In physics, these eigenvalues correspond to the possible quantized energy levels of the system, or they are then frequencies. So this would be the spectrum of the discrete levels of energy. And then this differential equation on the last slide can be formally solved. It just leads to exponential growth, which here is not the growth because it's multiplied by I. So it's just a rotation. There would not be the I, it would be exponential growth or decay. So, and this is a strange thing, right? It's like an operator in the exponent. Well, one can define this. This goes back a bit to Euler's formula, the same type of mathematics. If you expand this, write this as a series, as a Taylor series. You can define this strange object precisely. And for now, we don't need to bother. And we just say that this is just, we call whatever this is, operator U. So it's again a 2x2 matrix. And this operator U has a property that it's unitary. It doesn't change the length of the vector. It just rotates it and flips it. No, it just rotates it. So it means that it preserves length and angles at all times, and it's invertible. It's also an interesting feature in quantum mechanics. Whenever it's time reversible, so there's no information loss in quantum mechanics. As time progresses, U of t describes a flow in Hilbert space, and one can think of it as a rotation, and there's no stretching. And let's see how this looks in a picture. So we have our old quantum billiard balls, quantum marbles. And so let's take this blue state here and assume that the Hamiltonian is a diagonal matrix. Very simple. So what happens? Well, the blue state is an eigenvector already of this. So when you multiply this vector with this, it just gives the same vector. It doesn't even change its length. And then you can just start the dynamics in this state. It will not move because it's already in an eigenstate, so it will just acquire a complex space. So this expression, you can calculate it, and the dynamics is then described by this 2x2 matrix. So you see, it's just a complex space here. Lambda is a frequency. So it means this blue state will just oscillate. It will remain the same state, but it will just oscillate with this internal phase, which is not observable. So it will still move, but in a sense invisibly. But this motion it has defines its energy. yeah, so this is a way to describe it, and this is why Euler's formula was useful. It's a nice way to describe oscillations in the complex space. And we say that B is an eigenvector of H with the energy #1, and it oscillates in the phase space, which is not observable. So it means under this dynamics, a blue quantum marble will stay blue forever until something is measured. Say we measure whether it's purple or yellow, then of course it will be changed. But until we do this, under this dynamics, it just stays the same. So now let's assume a bit more structured Hamiltonian or more complex. So now this Hamiltonian has off-diagonal elements. And again, let's start with the blue as initial condition. And then again, here the eigenvalues of this and also of the U operator are now the purple and the yellow state. Okay? This means that if we start with the blue state, it will change in some way, which we will understand. So, as I mentioned, the purple and yellow state are the eigenvalues, eigenvectors. So if we would start with either of them, they would not change. But since we start with the blue, it will change. And okay, short. Okay. So let's see how the blue state will evolve under this dynamic. So we have to solve this Schrödinger equation with this initial condition. We again have to determine this unitary operator and be calculated. And it leads to this. It's a type of oscillation with a characteristic frequency 𝝀1, which was one of the eigenvalues in the slide before. And the solution is, if you start in the blue at t equals 0, well, the cosine of 0 is 1. So at t equals 0, this quantum state is blue, and the sinus of 0 is 0. So there's no red component. But as the time progresses, we will see an oscillation from blue to red to blue to red. This is what this dynamic is doing. So this state here will go here, then back.
So Michael, this can I ask real quick? In this case, this Hamiltonian is not meant to be the energy levels of the marble anymore, or is that?
No,
it's just a different.
Yeah, it could
right?
be, but it's and you could whatever self-adjoint operator. Any would do. So this is where in the quantum cognition context, we have more freedom to choose. We just need to respect the operator classes. So for this, only a self-adjoint operator would make sense. Otherwise, it changes, it messes up with the length. But in a physics setting, you would then be able to make the connection to the classical physics, and then typically here you would interpret it as an energy. But here in our context, you don't need anymore. It just gives you the frequency of whatever oscillation. So typically, this type of dynamics always leads to some kind of oscillation, and these oscillations have different modes. And each mode has a characteristic frequency.
Thanks.
But the connection to energy is not defined there anymore. Yeah, this is just representing that we will see oscillation from blue to red, and this happens also in this complex plane. So this is what is indicated here. So don't take it literally. the solution to the Schrödinger equation oscillates between blue and red around the eigenvector p with frequency lambda 1. There's 1 here. If we had we started out with p, it would just say p. Had we started with yellow, it would have remained yellow. Okay, and that's the last slide. So just how to think about solutions of the Schrödinger equation is always a form of rotation in Hilbert space with a characteristic frequency. And if you start with the eigenstate, the state will remain the same, but it will still rotate in its internal degree of freedom. And that's it. Is there any questions? Yeah, cool. And then Eva.
So
Please
what,
go first. Yeah.
I'm sorry, do you have a recommendation on a good textbook for this stuff? Is there?
Yeah, so
Is there one?
So the Busemeyer book, Peter Bruser, who talked today, and Busemeyer, they wrote this standard classical textbook on quantum cognition. This is good. And otherwise, maybe the book Jakub mentioned, the Susskind, right?
Yeah, I can recommend this, but it's quantum mechanics, so it's nothing about cognition, but it's a really good introductory encounter with quantum mechanics.
Who's the author of that one?
Leonard Susskind and Art Friedman. I can write it in the chat.
Thanks.
Thank you.
I can only confirm because I've read it. So in Polish language, it was translated. So it's a very good book. Yeah.
But for quantum cognition, I think the Busemeyer book. Maybe you can also write it in the chat because.
Yeah. So
it has roughly 50 pages on quantum mechanics and linear algebra and all what we talked about. So, and there may be also overview articles by maybe Potos. You know, the one about quantum cognition from Emmanuel Potos, the overview article by Busemeyer and Potos from last year. Maybe this is also a good place to start. I'm not sure. But you know, at the beginning, you don't need to worry too much about the dynamics. So it's not so often used. Because for this, to connect this to data, you would need to measure time series, and you would need to, this is another type of experiments, very complex. So people are more using the collapse of the wave function aspect and the non-commutativity of observables. So, and to understand this, you can do without the dynamics.
Yes, Eva, it's the right answer. I provided the link to Cambridge. And as was discussed today in the session, they are preparing updated version of it, but I think the promise was 22, so I don't know when to expect it.
Yeah, good. That's it. Then let's end here, and please make sure to come tomorrow to Jakub's session. Will be very good about quantum games. Good night.
Thank you very much. So good day.